Okay, hi everybody. So we're talking about the first law of thermodynamics today. I introduced it last time. First law of thermodynamics says that the energy of an isolated system is constant. Mathematically, delta U equals Q plus W. And what we're going to start talking about today is how we can calculate the change in energy associated with certain types of processes, heat transfers or work. And today we're going to talk about work. Okay, that's what we're interested in. Before I get into it, though, I need to tell you an important note, which is that work is a path variable. And path variables are fundamentally different than state variables. Everything we've talked about up to this point, temperature, volume, energy, are state variables. All I need to know is the temperature, and that's it. I don't care about where it was in the past. Path variables are different. And I thought I would illustrate this to you with a little drawing. So bear with me. Oh, can you tell what that is? It's a mountain. I lived in Colorado for a bit, so I like mountains. Here's the start. Person at the start. Here's the end. I'm going to just barely be able to get my person up on top. Okay. And the question is how does the person get from the bottom to the top? There are two different ways they could go. So the first way you could go would be like this. Sort of the free solo route. Just go right up the edge. The second way you could go is like this. Around and around and around, and the end at the top. Here's the question. If you go on a hike up a mountain, they usually tell you two things. The first is your altitude gain, and the second is the distance you hiked. So what kind of variable is altitude gain? Does it depend on these two different paths? Well, the answer is no, right? The altitude gain is a state variable. To know the altitude, you just need to know where you are in the mountain. And the change in altitude is only dependent on these initial and final states. It is the same for these two paths. The distance you hiked, however, is different. Right? The length that you walk is much longer on path 2 than on path 1. So the change is really dependent on how you get from point A to point B. Work is like that. Right? To correctly assess the amount of work that we do, we have to consider the path between initial and final states. So with that in mind, let's dig into it. What we're talking about here is gas expansion work. Right? And again, I'm going to try and draw a picture. I'm going to try and give as many physical images in your head as to what's going on. And so what we usually think about is a piston. Okay. Well, I got my piston off center, but there is some external pressure, right, which is forcing down the gas that's inside of here. The gas is going to expand. And the question we want to ask is, how much work does this do? I mentioned last time that the physics equation for work, is minus F external dx. A little sloppy, but I think you get it. Right? It's F dx. The dx in this is this distance here. Right? It's the change in the height of the piston. The Question is, what's the force? And it's a little less clear, but what you can do is multiply this by A over A, the area. And what you might recognize is that this quantity here, dxa, the area, is really a change in volume, right? So that cylinder has some area associated with it. And that's a change in volume. And this quantity here, force over area, you will no doubt remember, is pressure in color. So another way we can write this is minus P external dV. Okay. So another name for this type of gas work is PV work. Right? In other words, we're expanding the volume of the gas against some pressure, and there's a work associated with that. I'm going to show you some examples with my little gas cylinder, so bear with me. There are actually 4 different types that we'll talk about. They're shown here. We'll talk about 3 of them today, and then the last one I'll do later. All right, so first up, free expansion work. The starting point for all of these types of calculations is the formula that I just gave you, minus P external dV. This equation for work always works, haha. And what we need to think about is the path that the change occurs upon. Right? These different nomenclatures describe different kinds of paths. And so in a free expansion, P external equals 0. That's what I mean by a free expansion. So here's the model. I have my gas cylinder. I am going to stick my finger over the end of it. I pull the cylinder back and I ask how much work this does. I can't even get my finger on there. Hang on a second. No, this is even worse. There. Okay. Finger on it, pull back. How much work does it do? Well, you start plugging in 0 times dV. You remember from your calculus that this is 0. A free expansion does no work, and that makes sense. When I do this, there's no pressure inside of the cylinder, and let go, it just pops. It's a freebie. It does no work. 1 down, 2 to go. Constant external pressure. Work equals minus px dV. Again, this equation always works. Right? Here's a physical example of it. Here's my cylinder. I'm going to push down on this, if I can, until that gas is compressed in there, and I'm going to let go. The external pressure is 1 atm. Right? So the external pressure here is going to always be constant. And the question is, what's going to happen? Science is great. And as you'd expect, it just pushed itself back out. Okay. So again, I'm going to push this in until it's compressed a little bit. I let go, and it comes back. How much work does that process do? Well, if this is a constant, because the external pressure is constant, I can pull it out front of my integral. Okay. So minus P external integral of dV. And specifically, I'm evaluating this from V final to V initial. Integral of dV is V. And the way we most commonly write this is minus P external delta V. The amount of work that the gas does is minus P external delta V. Number 3, reversible isothermal expansion of an ideal gas. It's a long-winded title. There's lots of words in here that you'll recognize. Isothermal, ideal gas. There's an important new one, which is this guy, reversible. So what does it mean for a process to be reversible? A reversible change is one in which a change can be reversed by an infinitesimal modification in the opposite direction. So I can make a really small change in the opposite direction and the change is reversed. That's the formal definition. I think a more useful way to think about it is as following. In a reversible change, the system and surroundings are always in equilibrium. They're always balanced. So let me give you an example. This was the free expansion. If I can do this again. I've kept my finger over the end. There's no gas inside the cylinder, and I let go. Is this a reversible change? The answer is no, it's not. Right? The system, the gas inside the cylinder, and the surroundings are not balanced. It's not in equilibrium, right? And if I let go, I can't reverse that. There's nothing I can do to make it go back. In contrast, what I could imagine doing is slowly heating this thing up. And if I slowly heated it up and cooled it, right, what you might imagine would happen would be that this thing would just slowly expand. And in that scenario, these things would be in equilibrium, would always be balanced, and that's what reversible means. So keep coming up, but keep that on your radar screen. So away we go. I'm going to put my equation in. Minus P external dV. Because this is a reversible and the system and surroundings are always balanced, I can do the following. P external equals P gas. This is a reversible process, so the system and surroundings are always in balance, and I can make that equality. So now I get an expression that looks like this: work equals minus P gas dV. Right? Here's the issue. Pressure is a function of volume. In other words, P equals P of V, right? Pressure and gas are related. And so I need to explicitly put that dependence into this equation. And here's how you do that. Remember that I have an ideal gas. So if I solve for P, for an ideal gas, I will get P is nRT over V. I can now plug this in here. nRT over V dV. I pull out my constants. N's constant, R is a constant. What about temperature? It could, in theory, change, but it's isothermal, it's constant. So in fact, it won't. That allows me to pull this all out. Equals minus nRT integral of dV over V from VI to VF. Those of you who have the calculus in the forefront of your brain, Integral of dx over x, you may remember, is the natural log function. So this equation equals nRT natural log v, evaluated at v initial, v final, equals minus nRT natural log vf over vi. There you go. In summary, work is a path variable. We have to think about the way in which the change occurs in order to correctly assess work changes. We talked about these three kinds of changes: free expansion, constant external pressure, and a reversible isothermal expansion of an ideal gas. Check out the problems, and I'm actually going to make a little video to help you solve the first sort of worksheet problem and kind of walk you through that a bit. So pull that up, check out the video, and I'll see you next time.